Hey there, and welcome back to the Sleepless Scientist. Tonight, we're embarking on a journey into the very fabric of our universe, exploring a truth so profound it reshaped everything we thought we knew about reality. Before we dive in, if you enjoy these quiet explorations, please consider tapping that like button and subscribing. It helps us continue these late-night adventures. Now, settle in, get comfortable, and let's drift back in time. Imagine Europe in the mid-19th century, a time of grand invention, steam engines, and gaslight. Scientists, often working in dimly lit workshops, were wrestling with two mysterious forces, electricity and magnetism. For centuries, these phenomena seemed distinct. Static electricity crackled from amber, magnets pulled on iron. There were laws, yes, but they felt like separate chapters in an unfinished book, each telling its own story. Then, a series of curious observations began to hint at a deeper connection. A Danish physicist named Hans Christian Ørsted noticed something peculiar during a lecture demonstration. He saw that an electric current flowing through a wire could deflect a compass needle. Electricity, it seemed, could produce magnetism. This wasn't just a trick, it was a profound whisper of unification. This whisper grew louder with the work of Michael Faraday, a self-taught genius with an insatiable curiosity. Faraday wasn't just observing, he was experimenting meticulously, tirelessly. Faraday wondered if electricity could create magnetism, could magnetism create electricity? His experiments were elegant, involving coils of wire and moving magnets. He discovered that it wasn't just a magnet, but a changing magnetic field that induced an electric current. This was the key, not static presence, but dynamic change. Faraday introduced the concept of fields, invisible lines of force permeating space. It was a revolutionary idea, moving beyond action at a distance to something more tangible, yet unseen. While Faraday provided the experimental bedrock, the theoretical landscape remained fragmented. Scientists had a growing collection of laws, coulombs, amperes, Faradays, but no grand, unifying framework. This is where James Clerk Maxwell stepped onto the stage. A brilliant Scottish mathematician and physicist, Maxwell saw the scattered pieces of the puzzle and envisioned a complete picture. Maxwell's genius wasn't just in gathering existing laws, but in adding a crucial, missing piece. He realized that a changing electric field must also produce a magnetic field. He called this the displacement current. It was a theoretical leap, a symmetry that completed the elegant dance between electricity and magnetism, even in empty space. With this insight, Maxwell refined and unified all known electromagnetic phenomena into just four elegant equations. These weren't just descriptions, they were predictive tools. These equations, expressed in the language of calculus, described how electric and magnetic fields intertwined, how they generated each other, and how they propagated through space. Then came the truly astonishing part. When Maxwell manipulated his equations, a peculiar wave equation emerged. It described a self-propagating disturbance of electric and magnetic fields. Even more remarkably, the speed at which these electromagnetic waves traveled could be calculated directly from fundamental constants of electricity and magnetism. And that calculated speed, it was almost exactly the known speed of light. Maxwell had not only unified electricity and magnetism, he had revealed the true nature of light itself. Light, the very thing that allowed us to see the world, was an electromagnetic wave. It was a ripple in the fabric of these invisible fields, traveling at an astonishing, constant speed. This was more than just a scientific discovery, it was a profound shift in perspective. It suggested that this speed, the speed of light, was not just a characteristic of light, but perhaps something fundamental to the universe itself. The implications of Maxwell's work were immense. It paved the way for radio, television, and all wireless communication. But even deeper, it set the stage for questions that would challenge our very understanding of space and time. Maxwell's equations became the bedrock of modern physics. They were beautiful, consistent, and remarkably accurate, yet they also contained a subtle seed of a future mystery. If light always traveled at this constant speed, what did that mean for an observer who was moving? This seemingly simple question would lead to a revolution in physics, one that Maxwell himself could not have fully foreseen. Next time, we'll delve into this very question and follow the path of a young patent clerk who dared to challenge the established notions of space and time, forever changing our cosmic address. Until then, keep exploring. Maxwell's elegant equations had revealed light as an electromagnetic wave, moving at an astonishing, constant speed. This was a profound revelation, yet it presented a subtle challenge to the prevailing scientific worldview of the late 19th century. For every wave known, sound waves needing air, water waves needing water, there was a medium through which it traveled. It was an intuitive, deeply ingrained concept, a fundamental aspect of how reality seemed to operate. If light was a wave, what was its medium? Scientists proposed an invisible, all-pervading substance called the luminiferous ether. It was thought to fill all of space, allowing light to propagate. This ethereal ether was imagined as a sort of cosmic jelly, rigid enough to transmit light waves at immense speeds, yet permeable enough for planets to move through it without resistance. The existence of the ether seemed to offer a comforting explanation for light's journey through the vacuum of space. It was the background against which light's constant speed could be measured. If the Earth was moving through this stationary ether, much like a boat moves through water, then there should be an ether wind. This wind would affect the perceived speed of light. Light traveling with the ether wind should appear slightly faster, while light traveling against it should appear slightly slower. This difference, though minuscule, should be measurable. The challenge was immense, designing an experiment sensitive enough to detect such a tiny difference. It required unprecedented precision and ingenious thinking. Enter Albert Michelson and Edward Morley. Their goal was to directly measure Earth's velocity relative to this elusive ether, to finally confirm its existence. They devised an elegant instrument known as the interferometer. It was designed to split a beam of light, send the two resulting beams along different paths, and then recombine them. The apparatus was mounted on a massive stone block floating in a pool of mercury, designed to isolate it from vibrations that could distort the delicate measurements. One light beam would travel parallel to Earth's motion, theoretically experiencing the full effect of the ether wind. The other would travel perpendicular to it. When the two beams recombined, if there was any difference in their travel time due to the ether wind, they would create an interference pattern of light and dark fringes. Even a tiny shift in these fringes would indicate the presence and direction of the ether wind. It was a brilliant, precise method to detect the invisible. Michelson and Morley meticulously prepared their experiment. They understood the stakes, confirming the ether would solidify the classical understanding of the universe. They ran the experiment repeatedly, rotating the apparatus to observe light traveling in different directions relative to Earth's assumed motion through the ether. The measurements were taken with painstaking care, anticipating the subtle shifts that the ether theory predicted. The scientific community waited, expectant. But as the results came in, a profound silence began to settle over the lab. There was no shift, none at all. The expected interference pattern remained stubbornly unchanged. Light speed appeared constant, regardless of the direction it traveled or Earth's motion through space. The ether wind, if it existed, left no trace. This null result was baffling. It contradicted the intuitive understanding of waves and the very concept of an absolute frame of reference which the ether provided. The scientific community grappled with this unexpected outcome. Had the experiment failed, was there some flaw in the apparatus, or was the ether simply not there? The Michelson-Morley experiment, initially intended to prove the ether's existence, instead delivered a crushing blow to the theory. It was a mystery without an immediate answer. The universe, it seemed, was holding onto a secret. Light insisted on traveling at the same speed for everyone, everywhere, regardless of their own motion. This stubborn constancy of light's speed, revealed by the absence of an ether wind, became a profound puzzle, a crack in the foundations of classical physics. It was this very puzzle, this unyielding speed of light, that would ignite a revolutionary idea in the mind of a young patent clerk, setting the stage for a new understanding of space, time, and reality itself. Join us next time. The late 19th century was a time of unease in physics. Maxwell's equations beautifully described light, yet the Michelson-Morley experiment had left a profound silence. Light stubbornly refused to conform to expectations. The null result was a persistent riddle. If Earth moved through an ether, why was there no measurable ether wind affecting light's speed? The very foundations of physics seemed to tremble. Many brilliant minds tried to reconcile this. Perhaps the ether somehow dragged with Earth, or objects contracted in motion. Each attempt felt like patching a grand, elegant theory with increasingly complex exceptions. Meanwhile, in Bern, Switzerland, a young patent clerk named Albert Einstein pondered these very questions. He wasn't bound by the traditional academic pathways, allowing his mind to wander freely, unburdened by established dogma. Einstein approached the problem not by trying to explain away the Michelson-Morley result, but by embracing it. What if light's constant speed wasn't an anomaly, but a fundamental truth of the universe? It was a radical intellectual leap. Instead of building complex models to preserve the ether, Einstein chose to accept the stubborn facts and build a new understanding from them. He dared to ask, what if? His genius lay in his ability to strip away preconceived notions, to look at the universe with fresh eyes. He imagined simple scenarios, thought experiments, to test his ideas against intuition. From this deep contemplation, two simple yet profoundly powerful postulates emerged. They were not derived from complex equations, but declared as fundamental principles. The first postulate was the principle of relativity. It stated that the laws of physics are the same for all observers in uniform motion, regardless of their constant velocity. Imagine being on a smooth-riding train. If you drop a ball, it falls straight down, just as it would if the train were still. You cannot tell your absolute speed by performing experiments inside the train. This meant there was no preferred rest frame in the universe. No absolute stationary point from which all motion could be measured. All uniform motion was relative. The second postulate was even more audacious and directly addressed the Michelson-Morley mystery. The speed of light in a vacuum is the same for all inertial observers. This meant that whether you were standing still or moving toward or away from a light source at immense speed, you would always measure the light traveling at precisely the same speed. C. It was a universal constant, unaffected by the motion of the source that emitted it or the observer who measured it. Light's speed was absolute, a cosmic speed limit woven into the fabric of reality. This was the boldest stroke. It discarded the need for an ether, making its non-detection in the Michelson-Morley experiment not a failure, but an expected outcome. But accepting these two postulates together had profound, almost mind-bending implications for our understanding of space and time themselves. Classical physics had assumed space and time were absolute, unchanging backdrops against which events unfolded. Lengths were fixed, and clocks ticked at the same rate for everyone. If light's speed is constant for all and speed is simply distance divided by time, then something had to give. If c is always c, then distance and time could not remain fixed. This meant that observers moving relative to each other would measure different lengths and different durations of time. It defied common sense, yet it was the logical consequence of Einstein's postulates. Time itself could slow down for a moving observer relative to a stationary one. Distances could contract. These were not optical illusions, but fundamental changes in the very nature of reality. It was a gentle revolution, quietly dismantling the rigid framework of classical physics and replacing it with something far more fluid, more interconnected. Einstein's postulates didn't just explain the Michelson-Morley result. They provided a new, consistent framework for understanding motion at high speeds, where classical intuitions failed. This new understanding, known as special relativity, wove space and time into a single, unified fabric, space-time. They were no longer independent entities, but two aspects of the same reality. The cosmic speed limit of light, once a curious observation, became the fundamental constant that dictated how space and time would stretch and bend to accommodate it. Next time, we will delve deeper into these strange consequences, exploring how time truly slows, how distances shrink, and how our everyday experience of reality is merely a glimpse of a far more dynamic universe. Einstein's postulates, simple yet profound, had quietly shattered the classical understanding of space and time. If the speed of light was truly constant for all observers, then something else had to give. The universe, it seemed, was far more flexible than anyone had imagined. To grasp these startling implications, Einstein often resorted to thought experiments. These mental journeys allowed him to explore extreme scenarios, far beyond the reach of any laboratory of his time, to test the logical consequences of his ideas. One such thought experiment involved a simple light clock. Imagine two parallel mirrors facing each other with a single pulse of light bouncing back and forth between them. Each bounce marks a tick of this light clock. For an observer standing still right next to this clock, the light pulse travels a straight path up and down between the mirrors. The time for one tick is simply the distance divided by the speed of light. Now, imagine this light clock is placed on a very fast-moving train or a spaceship, traveling at a significant fraction of the speed of light. And imagine another observer standing still on the ground, watching this moving clock. From the perspective of the observer on the ground, the light pulse inside the moving clock doesn't just go straight up and down. Because the clock itself is moving horizontally, the light pulse has to travel a diagonal path. It traces a longer, zigzagging path from one mirror to the other as the clock moves forward. The light still travels from mirror to mirror, but the mirrors themselves are shifting horizontally during the light's journey. This is where Einstein's second postulate becomes crucial. The speed of light is the same for everyone. So the light pulse in the moving clock must still travel at c, even though it's covering a longer diagonal distance. If speed is distance divided by time and the distance covered by the light pulse is longer for the moving clock, but its speed remains the same, then the time it takes for one tick must be longer. This leads to an astonishing conclusion. For the observer on the ground, the moving light clock appears to tick slower than a stationary one. Time itself seems to be stretching for the moving object. This phenomenon is known as time dilation. It means that time does not flow at a universal, constant rate for everyone. It depends on your relative motion. The faster you move relative to another observer, the slower your clock will appear to tick from their perspective. Your own time, however, will always feel normal to you. Think of time not as a rigid, unyielding track, but as a gently flowing river. If you are standing on the bank, you see the river flowing past at a certain speed. Now imagine two boats on this river. One is drifting with the current, feeling its gentle push. The other is trying to row against it or perhaps speeding along with it. From your perspective on the bank, the boat's progress might seem different, but from inside each boat, the flow of the river might feel subtly different or even normal, depending on their motion relative to the water. Similarly, time itself is like that river. Its flow is perceived differently depending on your motion through the universe. This isn't an illusion, it's a fundamental aspect of reality. This concept, while counterintuitive, has been rigorously tested and confirmed. One of the earliest pieces of evidence comes from tiny particles called muons. Muons are created high in Earth's atmosphere by cosmic rays. They have a very short natural lifespan, decaying into other particles in mere microseconds. At their speed, they shouldn't be able to reach the ground before they decay. Yet many do. Their clocks are running slower due to their extreme speed, allowing them to travel much further from our perspective. Another compelling piece of evidence comes from the Global Positioning System, or GPS. The satellites that power GPS orbit Earth at high speeds. Their internal clocks, due to time dilation, tick slightly slower than clocks on Earth's surface. Without accounting for this relativistic effect, GPS systems would quickly become inaccurate by many kilometers each day. Engineers must constantly adjust for this time difference to ensure the precise navigation we rely on daily. It's a subtle, yet profound, confirmation of Einstein's insights. Time, then, is not absolute. It is relative, stretching and compressing depending on an observer's motion. This was a radical departure from centuries of scientific thought, yet it was consistent with the universe's behavior. But if time can be so fluid, what about space? Does distance also bend and shift in this dynamic cosmic dance? The implications of a constant speed of light continue to unfold. Next time, we will explore how this cosmic speed limit not only affects the flow of moments, but also the very shape of reality, revealing how lengths can contract and how energy and mass are intimately linked. Until then, keep wondering. Our journey through the cosmos has revealed that time itself is not absolute. It stretches and shifts, its flow dependent on an observer's motion. This was a profound, almost poetic, realization born from Einstein's simple postulates and the stubborn constancy of light's speed. If time, one of the fundamental pillars of our reality, could be so fluid, what then of space? Could distances, too, be relative? Could the very lengths of objects change depending on how fast they moved? The same logical thread that led to time dilation also demanded an answer for space. If the speed of light is always measured as c by any observer, regardless of their own motion, then both time and distance must adjust to accommodate this cosmic truth. This leads us to another astonishing consequence of relativity: length contraction. It suggests that objects in motion, when observed from a stationary frame of reference, appear shorter in the direction of their movement. Let's embark on another thought experiment, a mental voyage to understand this phenomenon. Imagine a very long spaceship designed for interstellar travel, passing by a stationary space station. From the perspective of an observer on the space station, the spaceship is moving at an incredible speed, perhaps a significant fraction of the speed of light. Meanwhile, an astronaut inside the spaceship experiences their journey as perfectly normal. Their own measuring devices, their own clocks, operate as expected within their moving frame. Now, let's consider how both observers would measure the length of the spaceship itself. This is where the constancy of light's speed becomes the key. The space station observer wants to measure the length of the passing spaceship. They might try to note the time it takes for the front and back of the ship to pass a certain point. Because the spaceship is moving and time is dilated for it from the station's perspective, a specific length measurement also becomes complicated. To reconcile the constant speed of light, something has to give. Imagine a light pulse sent from the front to the back of the spaceship. For the astronaut on board, the light travels a fixed distance in a specific time. But for the observer on the space station, the spaceship is moving forward as the light pulse travels. The light has to catch up to the back of the ship, which is receding. To ensure the speed of light remains c for the stationary observer, despite the spaceship's motion and the time dilation, the perceived length of the spaceship itself must shrink. This is length contraction. The length of an object, as measured by an observer who is moving relative to it, will appear shorter than its length measured by an observer at rest with the object. Crucially, this contraction only occurs in the direction of the relative motion. The height and width of the spaceship would remain unchanged, only its length along its direction of travel would be affected. So, if our interstellar spaceship were traveling past the space station at, say, 90% of the speed of light, the station observer would measure it as significantly shorter than its true length. This isn't an optical illusion, a trick of the eye. It is a fundamental, measurable change in the very fabric of space, just as time dilation is a real change in the flow of moments. And the symmetry of relativity holds true. From the perspective of the astronaut inside the spaceship, it is the space station that appears contracted in the direction of their relative motion. Our everyday experience doesn't reveal these profound changes because the speeds we encounter are infinitesimally small compared to the speed of light. The effects are negligible, unnoticeable. But at cosmic velocities, the universe reveals its true, flexible nature. Length contraction, alongside time dilation, paints a consistent picture of a reality far stranger than our intuition suggests. The profound realization is this: space and time are not separate, independent entities. They are inextricably woven together, forming a single, unified fabric called spacetime. You cannot alter your perception of time without also altering your perception of space, and vice versa. They are two sides of the same relativistic coin, constantly adjusting to maintain the cosmic speed limit of light. This challenged the very foundation of Newtonian physics, which had assumed a fixed, absolute space and a universally ticking clock. Einstein's relativity offered a dynamic, interconnected universe. The constant speed of light, once a peculiar observation, became the fundamental principle that dictated how the very dimensions of our reality, length, width, depth, and duration, would bend and shift. As we continue to unravel these mysteries, the universe reveals even deeper connections. Next, we will explore how this cosmic speed limit also links energy and mass, revealing the most famous equation in all of physics and the true power hidden within the heart of matter. Until then, keep your mind open to the wonders of reality. Our journey through the cosmos has revealed that space and time are not fixed, but fluid, stretching, and shifting depending on an observer's motion. The universe, guided by light's constant speed, revealed its flexible nature, challenging centuries of intuition. Einstein's special relativity profoundly reshaped our understanding of dimensions, but the implications of a universal speed limit extended even further, touching upon the very essence of matter itself. What other secrets did C hold? As objects approach the speed of light, not only do time and space behave strangely, but another fundamental property also changes in a surprising way. This property is mass. Imagine trying to push a cart. It gets harder to push the faster it goes. Now imagine a particle accelerating close to the speed of light. As it gains speed, its effective mass increases. This isn't just a theoretical concept, it's observed in particle accelerators. As particles are pushed to incredible speeds, they become more massive, requiring increasingly more energy to accelerate them further. This increase in mass makes it impossible for any object with rest mass anything that isn't light to ever reach the speed of light. It would require infinite energy to accelerate an object of infinite mass. This relativistic increase in mass was more than just an interesting observation. For Einstein, it was a profound hint at an even deeper connection, a fundamental equivalence between mass and energy. From the bedrock of special relativity, Einstein derived one of the most famous and impactful equations in all of science, E equals mc2. It stands as a testament to profound insight. This equation states that energy E is equal to mass m multiplied by the speed of light squared c2. It reveals that mass and energy are not separate entities but fundamentally interchangeable. Imagine them as two different forms of the same cosmic substance. Mass can be converted into energy and energy can solidify into mass. It's a cosmic exchange rate. The C2 term is crucial. The speed of light is an enormous number, and when squared, it becomes astronomically large. This means even a tiny amount of mass can yield an immense amount of energy. This profound relationship explains the immense power unleashed in nuclear reactions. It's the engine that powers stars and nuclear power plants, turning subtle changes in mass into powerful energy releases. In nuclear fission, the total mass of the products is slightly less than the initial mass of the reactants. That tiny, missing mass hasn't disappeared, it has been converted directly into energy. Similarly, in the heart of stars, hydrogen atoms fuse to form helium. The resulting helium atom has slightly less mass than the original hydrogen atoms. This difference, though minuscule, fuels the sun's brilliance. E equals mc2 isn't just about explosions, it's a fundamental statement about existence. It tells us that matter itself is a highly concentrated form of energy, waiting to be unleashed or transformed. It means the very atoms that compose our bodies, the air we breathe, and the distant galaxies are all, in essence, bundles of frozen energy, bound by incredible forces. This equation also helps us understand light. Light, or photons, have no rest mass, yet they carry energy and momentum. This is consistent with E equals mc2, where energy and mass are interlinked. The discovery of this equivalence fundamentally changed physics, linking concepts that once seemed entirely separate. It was another thread woven into the tapestry of a unified universe. It provided a deeper understanding of creation and destruction, of how the universe's most powerful events, from the birth of stars to the decay of radioactive elements, operate. The cosmic speed limit of light, c, became more than just a constant for wave propagation. It became the ultimate conversion factor, the bridge between mass and energy. This revelation was a profound moment in scientific history, opening doors to previously unimaginable technologies and a deeper philosophical understanding of reality. But if mass and energy are interchangeable, and if energy is a fundamental component of the universe, what further secrets does this intimate connection hold? Could this equivalence influence the very fabric of spacetime itself? If mass bends spacetime and mass is energy, then does energy also bend spacetime? This question would lead Einstein to his next great leap, a theory that would describe gravity not as a force, but as a curvature in the very geometry of spacetime. Next time, we will explore this ultimate revelation, the universe's grand design, where mass, energy, space, and time intertwine in a cosmic dance of gravity. Until then, keep your gaze fixed on the wonders above. Our previous explorations revealed that mass and energy are two forms of the same cosmic substance, interlinked by the square of light's speed. This profound equivalence hinted at an even deeper structure underlying reality itself. If energy could bend spacetime, as Einstein's later work would suggest, then the very geometry of our universe was far more dynamic than previously imagined. The question remained, how could we visualize this bending, this intertwining? Classical physics had treated space as a fixed stage and time as a universally ticking clock, separate and independent. But special relativity had begun to blur these lines, showing they were not so distinct after all. It was Hermann Minkowski, one of Einstein's former mathematics professors, who provided a profound geometric interpretation. He saw that space and time were not merely related, but fundamentally interwoven. Minkowski declared that henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. This union he called spacetime. Spacetime is a four-dimensional fabric combining the three dimensions of space with the one dimension of time. Every event in the universe, from a star's birth to a dropped pen, occurs at a specific point in this fabric. While we cannot easily visualize four dimensions, we can use diagrams to represent them. Imagine time as one axis and space as the other two, collapsing one spatial dimension for simplicity. From any given event in this spacetime, light emanates outwards in all directions. As it travels, it traces a specific path, expanding like ripples on a pond. Because light always travels at the same constant speed, its path forms a distinct geometric shape in spacetime, a light cone. This cone is not arbitrary, it is fundamental to how reality is structured. Imagine an event happening right now at a specific point in space and time. This event is the vertex of our light cone. From this point, light expands outward, defining the cone's boundaries. The upper part of the cone, extending into the future, represents all the places and times that light from our event could reach. The lower part, extending into the past, represents all the places and times from which light could have reached us. This geometric structure, the light cone, becomes a powerful tool for understanding cause and effect in the universe. It dictates what can influence us and what we, in turn, can influence. Consider the lower half of the light cone, often called the past light cone. This cone encompasses all events in spacetime from which a light signal or any information could have reached our central event. Any event that lies outside our past light cone cannot, by the laws of physics, have influenced us. The information simply could not have traveled fast enough to reach us, even at the speed of light. It's like dropping a pebble in a pond. The ripples spread outwards, defining a region of influence. Anything outside those ripples remains unaffected by that particular pebble. This means our present reality is shaped only by events within our past light cone. The universe outside this cone, while existing, is causally disconnected from our immediate experience. This concept reinforces the cosmic speed limit. No information, no influence, no cause can propagate faster than light. It's a fundamental barrier woven into the fabric of spacetime. Our observable universe, the part from which light has had time to reach us, is essentially defined by the extent of our past light cone, stretching back to the Big Bang. Now, consider the upper half of the light cone, the future light cone. This represents all the events in spacetime that our central event or our actions can causally influence. Any action we take, any signal we send, any information we transmit can only reach locations and times within this future light cone. Beyond its boundary, our influence simply cannot extend. The light cone, therefore, defines our sphere of influence, both receiving and sending. It's a fundamental statement about what is knowable and what is achievable within the universe. It implies a profound determinism, not in the sense of fate, but in the sense that our reality is bounded by the speed of light. What we perceive and what we can do are intrinsically limited by c. The light cone is a geometric expression of causality itself. It shows that the past is fixed and the future is open, but both are constrained by the universe's ultimate speed limit. This elegant concept beautifully integrates the constancy of light speed into the very structure of spacetime, giving us a visual framework for understanding our place in the cosmic dance. But what happens when immense mass and energy warp this very fabric? Next time, we will delve into how gravity itself is not a force, but a curvature of spacetime, revealing the grand design of Einstein's general relativity. Special relativity had elegantly described the universe for observers in uniform motion. It had woven space and time into a single fabric, a dynamic tapestry where length and duration shifted with speed. Yet, a fundamental piece of the cosmic puzzle remained outside its grasp. Special relativity was a theory for flat spacetime where there was no gravity. It couldn't explain why an apple fell from a tree or why planets orbited the sun. It only applied to situations without acceleration. Einstein knew this limitation. His goal was to extend his revolution, to incorporate gravity into this new, flexible understanding of spacetime. This was a far more formidable challenge. Newtonian gravity for centuries had described gravity as an instantaneous force. A change in the sun's position, for example, would immediately affect Earth. This contradicted the cosmic speed limit. If nothing could travel faster than light, then gravity, too, must have a finite speed. This inconsistency was a deep source of unease for Einstein, a fundamental crack in the existing framework. For nearly a decade after his special relativity papers, Einstein grappled with this problem. It was a period of intense intellectual struggle, filled with false starts and profound insights. Then, in 1907, came what he later called his happiest thought. He was sitting in his patent office chair, pondering the nature of gravity. He imagined a person falling freely in an elevator. What would they feel? They would feel weightless, just as if they were floating in the vast emptiness of space, far from any gravitational pull. This simple thought experiment revealed a profound equivalence. The effects of gravity were indistinguishable from the effects of acceleration. Conversely, a person in a rocket accelerating upwards would feel pressed to the floor, exactly as if they were standing on Earth under gravity. This principle of equivalence became the cornerstone of his new theory. It meant that gravity wasn't a force pulling objects, but a consequence of the geometry of spacetime itself. It was a revolutionary way to think about gravity, transforming it from a mysterious force into an intrinsic property of the universe's fabric. Imagine spacetime not as a rigid, unchanging stage, but as a flexible, elastic sheet. The presence of mass and energy would cause this sheet to warp and curve. This curvature, this bending of spacetime, is what we perceive as gravity. Planets don't orbit the sun because they are pulled by a force, but because they are following the curves in spacetime created by the sun's immense mass. It's like rolling a marble near a bowling ball on a trampoline. The marble isn't pulled by the bowling ball, it simply follows the curved path created by the bowling ball's weight. The more massive an object, the greater the distortion it creates in spacetime. This explains why massive stars and black holes have such powerful gravitational effects. To describe this complex curvature mathematically required new tools. Einstein had to delve into the realm of differential geometry, a field pioneered by Bernhard Riemann. This was the arduous part of his journey, translating his profound physical insights into a rigorous mathematical framework. He collaborated with friends and mathematicians, learning the necessary language. Finally, in 1915, after years of intense effort, Einstein presented his field equations of general relativity. These equations described how matter and energy warp spacetime and how spacetime, in turn, dictates the motion of matter and energy. General relativity was a triumph, a grand unification of gravity with the fabric of spacetime. It explained planetary orbits with unprecedented precision and made startling new predictions. One of these predictions was the bending of light by massive objects. Light, though massless, would follow the curves in spacetime, causing stars to appear in slightly different positions when their light passed near the sun. This prediction was famously confirmed during a solar eclipse in 1919 by Arthur Eddington, catapulting Einstein to global fame. It was direct evidence of spacetime's flexibility. Even in this grand new theory, the cosmic speed limit remained paramount. If spacetime could curve and these curves could change, how fast would these changes propagate? Einstein's equations predicted that disturbances in spacetime caused by accelerating masses, like two black holes spiraling into each other, would generate gravitational waves. These ripples, these gravitational waves, were predicted to travel at precisely the speed of light. The ultimate speed limit, c, extended its dominion even to the very geometry of the universe, a silent testament to its fundamental role. Next, we'll see how these waves were finally detected, revealing the universe's deepest whispers. As our journey through the universe's profound truths nears its close, we pause to reflect. The night deepens, and with it, our understanding of the cosmos has grown, shaped by the quiet perseverance of curious minds. We began by tracing the invisible threads of electricity and magnetism, patiently observed and meticulously documented, until their hidden dance was revealed. Light, a familiar presence yet a profound mystery, became our guide. Its nature, its speed, and its unwavering constancy held the keys to unlocking deeper secrets of reality. It was James Clerk Maxwell who first saw the elegant symmetry, unifying these forces into four beautiful equations. He showed us that light itself was an electromagnetic wave, a ripple in these invisible fields. From these equations, a speed emerged, calculated from fundamental constants. It was the speed of light, an astonishing velocity, suggesting a universal constant long before its full implications were grasped. Yet this constant speed presented a puzzle. If light was a wave, what was its medium? The prevailing idea of a luminiferous ether filled the void, but it remained elusive. The meticulous experiment of Michelson and Morley sought to detect this ether wind. Their apparatus, delicate and precise, was designed to reveal the subtle shifts. But the results were stubbornly null. Light's speed remained constant, regardless of Earth's motion. The ether, it seemed, did not exist. This was a profound silence, a challenge to classical intuition. Then a young mind, unburdened by convention, dared to embrace this stubborn fact. Albert Einstein, in his quiet reflections, chose to accept light's constancy as a fundamental postulate. His two simple postulates, the laws of physics are the same for all in uniform motion, and the speed of light is constant for all observers, became the bedrock of a new reality. Special relativity was born, a theory that revealed the universe to be far more fluid, far more interconnected than previously imagined. Space and time were no longer independent. The consequence was astonishing. Time itself stretched. For objects moving at high speeds, clocks would tick slower, a phenomenon known as time dilation, confirmed by tiny muons and precise GPS satellites. And space, too, responded. lengths would contract in the direction of motion, a subtle compression of reality to maintain light's unwavering speed. Distance became relative, not absolute. The cosmic speed limit, c, also linked mass and energy in the most profound way. E equals mc2 revealed that matter itself is a concentrated form of energy, a powerful truth powering stars and shaping the universe. These revelations culminated in the concept of spacetime, a four-dimensional fabric where every event holds its place. The light cone, a geometric expression, defines what can influence us and what we can influence. Finally, Einstein extended his vision to include gravity. It was not a force, but a curvature in this very fabric of spacetime, caused by the presence of mass and energy. Even the ripples in this fabric, gravitational waves, were predicted to travel at the speed of light, a testament to c being the ultimate cosmic speed limit for all interactions. Tonight, we've journeyed through these profound truths, from Maxwell's elegant waves to Einstein's revolutionary insights into curved spacetime, all converging on the constancy of light. The core implication remains: light's constant speed means a universe where space and time are not fixed, not absolute, but fluid, dynamic, and intimately interconnected. Our reality is not a rigid stage, but a responsive, ever-adjusting dance of dimensions, all harmonized by this single, unwavering speed. This journey is a reflection of the beauty and persistence of scientific inquiry, the human desire to understand, the patience required, and the profound revelations that curiosity can unlock. Each step, each observation, each patient experiment built upon the last, slowly revealing the grand design of the cosmos, one layer at a time. The cosmic speed limit, c, is more than just a number. It is the fundamental constant that not only defines the speed of light, but fundamentally shapes the very structure of our reality. It dictates how events unfold, how information travels, and how we perceive existence itself. It is a quiet, universal truth, inviting ongoing peaceful contemplation. And so, as the moon climbs high, casting its soft glow upon our world, we leave these cosmic mysteries to linger in your thoughts. Sleep well, and may your dreams be filled with the quiet wonder of the universe.